Bismillahirrahmanirrahim. I am Professor Jamil and you are watching YouTube channel. Today we are going to take up a question. This is an in fact exam question and it is about the Laplace transform. Here is the simple statement. Compute Laplace transform of second derivative of the function f. Earlier in my video, in fact in my lecture, I computed the derivative Laplace transform of the first derivative of f. Now it's the turn for second derivative. Let's check how can we find it. So first of all, there is a heading for solution and you need to find Laplace transform mean L of this d2f by dt square. You need to find its value and take Laplace transform of d2f by dt square, and this is equal to L is an operator which is an integral operator, and this integral means there will be some integration variable, and integration variable would be t because f is a function of t. That is why it is differentiated with respect to t. So when f is a function of t, that t will be integrated here from 0 to infinity and dt. This is integration variable. Then there is a kernel e to the power minus st, where s is the new variable and t is the old variable, right? And here you write the function whose Laplace transform is required, and you require the Laplace transform of this thing. This you can write in simple notation as ft, where f double dash or double prime t is d2f by dt square. Now you have a definite integral and there are two factors in it, factor number 1 and factor number 2. In factor number 2 you have the derivative of the function f. So where you have the derivative, you take it as second function and this one as the first function and integrate by parts. By parts, integrate by parts. Okay, so left side is same as before, d2f by dt square, and this one first function into integration of the second function or second factor, whichever you like. And integration means one derivative will be erased from here, so you will have f prime of t and apply the limits of integration, which are from 0 to infinity. Minus integral sign mean integration with respect to t. Okay, first function into integration of second minus integration of second, and integration of second mean this is the second function. Its integration means the one operator for derivative mean one prime will be erased and you will have f prime. Double, instead of double prime you have f prime. So first function, listen again, into derivative of this second function here minus integral into integration of second function into derivative of the first function. So derivative of this exponential is the exponential into derivative of the exponent, this exponent, and it is minus s. Okay, done. Now you apply the limits. E to the power minus s into infinity into f prime infinity minus e to the power s0 into f prime 0, and this minus minus makes plus, s will be taken out because it is a constant with respect to the integration variable t, so it is out, and you have t from 0 to infinity and dt f prime t and e to the power minus st. Again here you have a product of two factors and here you have derivative. It will be your second function and this is the simple exponential. It is your first function and you will integrate once more. Integrate by parts once more. Now here If your s is positive, then positive number multiplied with minus will be minus, and into infinity mean minus infinity, and e to the power minus infinity is 0. E to the power minus infinity is 0. So let's write it. Let's write it here. Here. Okay, let me erase this line because we don't need it again. So on the left is Laplace transform of d2f by dt square, and here you have 0 f prime infinity. F is a finite function because its derivative is exist. Look, if f is continuous and finite, then it can be differentiated with respect to t, and if this is continuous and differentiable, it can be further differentiated with respect to t, and this makes d2f by dt square. So when you are given d2f by dt square and you are asked to find its Laplace transform, it means your f is a continuous function and a differentiable function, and the continuous and differentiable functions are always finite functions, which means value of the derivative at infinity is a finite number. So 0 into finite number will be 0. Okay, or if one time you can write it 0 into f prime infinity. In the next line you will make it 0 minus, this is 1, e to the power 0 is 1, into f prime 0 and plus s, and next you have again integration with respect to t and do by parts. First function e to the power minus st, this is your first function. First function into integration of the second function. When prime is integrated, the prime will be vanished. You will have f only, and you need to apply the limits again, t from 0 to infinity. So listen again. First function as it is into derivative of the second function. Sorry, first function into integration of the second function, and when prime is integrated, prime means derivative, then derivative operator vanishes, then you get the function minus integral over t mean dt is here, and now read again. First function into integration of second, minus integral into integration of second, and integration of second means integration of f prime, and when prime is integrated, then you will have no prime here. Integration of second into derivative of the first, and derivative of the first means derivative of the exponential, which is exponential, into derivative of the exponent mean power. So it is minus s, and you are done. Close the bracket now. Now this is a 0 because f prime, and this means s is greater than 0, because if s is not greater than 0, then this minus, for example, if s is negative, mean less than 0, then this negative and this negative will make positive, and e to the power positive into infinity means e to the power plus infinity, and that will make here infinity, and that infinity will make everything as infinity, and you will not have finite answers. So this piece tells you that s should be a negative number. So your new variable s, which was introduced to the Laplace transform, is positive number, and this is the finite number, so this is 0 minus f prime 0 and plus s, and here use the limit again, e to the power minus s into infinity into f infinity minus lower limit e to the power minus s into 0 into f of 0, and this minus minus makes plus s into t0 to, this is 0 to infinity dt ft into e to the power minus st. And now this factor has been made 0 because f dash infinity is finite. Mean f prime is a continuous function, which means f prime has finite value. So forever, for whatever t we use, just as t is infinity. So the important thing is that f prime is finite because f prime says f is a continuous function. Okay. Or you can say f prime is this, and you can take its derivative to make this, which means f prime is a differentiable function, and whenever you have a differentiable function, then its value for any value of the variable t will be finite. Mean f prime is finite whatever is the value of t. So I am saying f prime is a finite number. Okay, now you have minus f prime 0 and plus s here. You have, this is e to the power minus infinity, again 0 into f infinity, minus this is 1 into f0, and plus s, and you can write this with a little rearrangement, dt kernel first into ft, and this is your L, it is acting on t, mean this is the Laplace transform of t. Okay, now this is minus f prime 0 plus s, and this is 0 because f infinity is finite. Look, if f infinity was infinity, then infinity multiplied by 0 is indeterminate, right? Be careful. This thing needs to be explained carefully. Okay, so listen again. If f infinity is infinity, mean value of the function when t is infinity is infinite, then infinity multiplied by 0 will be indeterminate, mean no answer is possible here. That's why I am stressing again and again on f infinity, just as I have stressed on f prime infinity. Okay, so this is 0. If f infinity, listen again, is not finite, then if it is in other words infinity, then infinity multiplied by 0 will be infinity. Indeterminate. Indeterminate means you have no answer here. And when you have no answer here, it means you have no answer within these square brackets. Right? Minus f0, and this is plus s into this whole thing. This is the operator L, this whole, right? And it is acting on function ft. So it becomes Laplace transform of ft. Now you expand the bracket. This is minus s into f0. This is plus s square into Laplace transform of ft. And you should write here this f, because f infinity is finite, right? Why it is finite? Due to existence of d2f by dt squared, whose Laplace transform has been asked to you, right? So only the finite functions will have the Laplace transforms. So the finite number multiplied by 0 produces 0. So you have the next line. And on the left you have Laplace transform of d2f by dt squared. Now you can rewrite this line as Laplace transform of Laplace transform of d2f by dt square is equal to, first write this s square term into Laplace transform of ft, then write the term whose s term has exponent 1, which is this minus s1 into f0, and then minus s0. S0 will make 1 minus 1. So this is minus s0 into f prime 0. So this is your formula for the Laplace transform of the second derivative. And please note it carefully. This argument and this argument is very essential to get a 0 here and 0 here. Right? If you do not understand or report this argument, mean this reasoning, then the examiner may deduct your 1 or 2 marks. So be careful. Now this is the Laplace transform for the second derivative, and I suggest you to remember this formula because this formula is quite helpful while solving the linear differential equations with constant coefficients by using the Laplace transform method. Thanks for watching. Keep watching and please like, share and subscribe this channel with your friends and family so that such questions from the past papers of the universities and many others comes to you in the first place. Thanks for watching.